Hello class, I hope your lunch was great. Today we are going to be talking about rock climbing.
Rock climbing?
Yeah, it's unbelievable how packed it is with physics.
Be prepared and pay attention to this incredible lesson about the extreme sport of rock climbing.
So the three topics that we are going to be covering today are number 1, friction and good skin to grip the wall. Number 2, gravity and tension forces acting on the climber. And number 3, modeling the rope as a spring to measure stretch.
The first situation is a hand with no chalk. It has a high coefficient of static friction, but when the hand begins to sweat, it'll start to slip off. This lowers its μs. This climber has a sweaty hand. They're having a difficult time gripping the rock. The hand with chalk will originally have a smoother surface, lowering its μs, but as it absorbs sweat, it gives a better grip and increases its μs. Here, the climber is applying chalk to their hand through the chalk bag. We can see that their hand has a better grip onto the rock. Now, we have to draw a free body diagram of a hand with chalk gripping onto a rock onto the wall. We can assume that this rock sits at a 45-degree angle. Now, with our coordinate system, we can draw the forces acting on the object. These are the forces of gravity, the normal force, and the static friction force. We are required to find the values of all three of these forces. But first, we must split the normal force and the static friction force into their x and y components because they are not parallel to the coordinate system. As well, we must assume that their angles are both 45 degrees. Next, we need to find the sum of the forces in the y direction. Because this hand has a strong grip on the wall, we can assume that the acceleration is 0, allowing us to set this equation equal to 0. We can also assume that Fny and Ffsy are equal to each other because they both use the same angle. Now, rearranging this equation for x and plugging in the numbers that we know, we can come to a final answer of 245. Now, for the normal force. We can take this triangle from our free body diagram. We can label all the sides as well as the angles. And we have chosen to name this bottom angle theta. Setting up our equation that cos theta equals adjacent over hypotenuse, plugging in the sides that we know, rearranging for the normal force, and plugging in the values that we know, we can come to a final answer of 346.48 newtons. Now, we must do the same thing for the static friction force. We can take this triangle again from the free body diagram, label its sides as well as its angles, and choose that this angle will be theta. Setting up the same equation, cos theta equals adjacent over hypotenuse, plugging in the sides that we know, rearranging for Ffs, and plugging in the values that we know, we can come to an equal answer of 346.48 newtons. Therefore, we can conclude that the normal force is equal to the static friction force. And finally, solving for the force of gravity. We know that gravity is always equal to negative mg. We know both of these values, allowing us to come to an answer of negative 490 newtons.
Now I know that was a little hard, but class, do you understand?
Yeah, that was incredible. Teach me more.
Now, we need to find the height of the wall. We know that it is 50 feet, and after converting that to meters, we can divide it by 3 to find the height for each section.
This is the climber being belayed down. For approximately the first 5 meters, they are accelerating downwards. Then for the next 5 meters, they are moving at a constant speed. And for the final 5 meters above the ground, they are slowing down.
Now, for the first scenario where the force of gravity is larger than the tension force, we know that we are accelerating downwards. After writing everything that we are given and assuming that the acceleration is 0.5 meters per second squared, we can set up for the third kinematics equation. We are going to be solving for v2y. The first step is to isolate this. Then we must plug in all of the numbers that we know. We are going to be going from 15 meters to 10 meters. After going through all of the steps, we can finally come to an answer that v2y equals 2.24 meters per second. The second situation has a tension force that is equal to the force of gravity. Therefore, the climber is being belayed down at a constant speed. Here, we are going to use the final velocity from the last scenario as our initial velocity. We are going to be going from 10 meters to 5 meters, and we are solving for the time that it takes. We come to a final answer of 2.23 seconds. Now for the third situation, the tension force is larger than the force of gravity, giving an upwards acceleration, slowing down the climber at the end of their climb. We can assume that their acceleration is 0.2 meters per second squared. Now to find the magnitude of the tension force, we must first find the sum of the forces in the y direction and set it equal to MAY because there is an acceleration. After isolating for Ft and plugging in all the values that we know, we can come to a final answer of 500 newtons.
Whoa, I didn't know belaying down could be so complicated.
Now for our third concept, the spring force. Beach, do you want to come give it a try?
Yeah, sure, I'd love to.
To solve for k, the spring constant, we must first draw a simple free body diagram and label the forces Fg and Fs. The length of the rope stretch is 15 meters times 1.05, since the length of the rope can extend 5% from the 15 meters.
Here, a climber is falling off of the wall. It is obvious that the rope can extend a considerable amount from its original length to break his fall.
Some of our given information that we can use is the mass of the climber, which is 50 kilograms, the gravitational constant, which is 9.8, and delta x, which can be calculated doing length of the rope stretched minus the length of the rope unstretched. This then gives us 0.75 meters. After doing this, we can sum up our forces in the y direction, and since we know that the acceleration is 0, this means that the sum of the forces is equal to 0. Since Fg is equal to negative mg, this means that Fs is equal to positive mg. After doing this, we can isolate for the spring constant since we have all the required variables. We can do k equals Fs over delta x, which is then mg over delta x. Since we have all these values, all we must do now is plug in the numbers, and this gives us 653.33.
And that's the end of our lesson, class. I hope you all got your notes down. And by the way, I have good news. Tomorrow, we're going rock climbing!